One other important topic, or something to know about crystalline materials, is that there are what's called imperfections in the atomic structure of crystalline materials. So imperfections or defects in materials, crystalline or otherwise actually, are inevitable in that no material that is large enough is defect free or is atomically perfect, in the sense that it has the elemental purity that one believes it to have. Hence, it has some sort of impurities, or it has some sort of problem with the arrangement, with the order of its atoms, the way they come together, the way they space themselves. So there is always, in every material that's large enough, meaning any material that's not very, very, very small and made in very controlled conditions in a laboratory, even then there are imperfections. They're just fewer than regular. And in real material, there are large numbers of imperfections. So it is possible to use this idea or this concept or this knowledge of imperfections to discuss different types of problems, or let's not say problems, but deviations from perfection that exist, that arise in solid materials. It is possible to discuss the number and types of these and whether they can be controlled. So whether you can decrease or increase the number of occurrences of imperfections in a material. By knowing what these are and what they can do, how they can affect a material property positively or in a way that we want it to be affected. Is this possible? Can this be done? Or how can this be done? So because of this, are all defects undesirable, or can you have so-called desirable defects? And how do defects in certain materials like ceramics differ from defects in other materials like metals? So lots of these questions can be answered, maybe not immediately after having reviewed these slides, because you'll notice that these slides are a very brief introduction to the concept. The goal of this slide set is to introduce to you that there are zones of imperfection, and they can have effects. They can have effects on the properties of materials. But after having reviewed these slides, you won't necessarily become an expert in crystal defects. But so defects are deviations from perfect atomic arrangement in a crystal, meaning in 3 dimensions, if you have an FCC type of repeating structure, this requires that throughout the whole crystal, you have the same distance between 2 atoms in a chosen crystal direction. So you remember from the previous slide set that you know what a direction is, and you can label them using 3 numbers, indices, and along that chosen direction or along a chosen plane, you would expect to have, in a perfect crystal, you would have the same distribution of atoms. Whereas if you start moving along a certain direction and you suddenly encounter a an unexpected distance between two atoms, or an unexpected atom elementally, meaning an atom that doesn't belong there. This would be these two would be examples of deviations from perfection. And if it's important now to state that often defects in materials are added intentionally by the people who are using those materials to obtain slightly modified materials with better properties. An example of which may be, say, higher conduction, electrical conduction, or better, higher strength mechanical properties. Many examples exist. And in general, in civil engineering materials, we try to add defects intentionally to improve mechanical properties in ways that will benefit us when we're trying to use those materials. So in a metal, by adding another metal in some small amount, you can obtain an alloy. An alloy is when you have two or more metallic elements combined, and the way this is done is that the smaller amount of the second or the third type of metal that you add to the first type of metal creates a bunch of defects. So we'll see a little sketch of this in a few slides. So among the properties that can be controlled by imperfections, you could count the conductivity of some semiconductors by small trace amounts, meaning very small amounts of certain chemical impurities. So you add chemical impurities in this field referred to generally as dopants, so materials that dope the parent material. So the color or luminescence of various crystals also is related with impurities. So an example of this is a diamond. So a diamond, as you probably know, is it would look like glass. It would be very clear. It would be translucent if not for impurities. The fact that there are other colors of diamonds, such as yellow diamonds or pink diamonds, like in the movie Pink Panther, is due to certain elements and their atoms being present in some small quantities inside the carbon three-dimensional network that gives you diamond. So these impurities or these foreign atoms would probably influence, or would definitely influence, the mechanical properties of diamond, such as its strength, but it would also influence other properties. And you may imagine that certain properties may change in a way that makes you happy, that is beneficial. In certain ways, in certain properties, there may be a decrease, but depending on what you are after, the value of the material or the usefulness of the material could change positively. So the process of diffusion, atomic diffusion, is also accelerated by impurities in a material. And mechanical properties, or here what's referred to as plastic properties, will later be introduced as the ability to change the shape of the material. So for a metal to be able to bend is here what's referred to as the plastic property. So the ability to bend or not be able to bend, the inability to bend, will also be related with the amount and type of imperfections in the material. So fortunately, the slide states, crystals are seldom, if ever, perfect. So this is to emphasize the idea that when a material has defects, it is generally better. Here it says stronger. You might think of it as better in not only mechanical ways, but in many other ways. So knowledge of how to change properties, or how not accidentally to change properties, is, of course, of importance in this field. So imperfections in a crystal are defined according to size or according to dimensionality. So in the first, in the dimensionality method, you have 0, 1, 2, or 3 dimensions. So 0 dimension is a point, and these defects are referred to as point defects, and there are various examples of these. We'll see some of them in the following slides. In 1 dimension, which is a line, we have line defects and examples of that. In 2 dimension, which is an area or a surface, in 2 dimensions we have surface defects or interface defects, interfacial defects, between 2 faces, between where 2 faces meet each other, you may think. And in 3 dimensions, so you have a volume, hence you have what's referred to as a volume defect or a bulk defect. And we'll see examples of these in the slide set. So according to sizes, you may imagine that a point defect is the smallest because it's either an electron problem or a defect, or it's an atom defect. So if it's an atom defect, it has a size of approximately 0.1 nanometers, because 1 angstrom, or 0.1 nanometers, is the size that we take as sort of the average atomic size. You may be a little larger, you may be a little smaller, but about this size. And you know this because we had found the interatomic spacing in our examples of bonding in the previous slide sets as, say, 0.3 nanometers. So we know that we're around that size range. For electrons, meaning you have 1 problematic electron, you have too many electrons, something wrong with at the electron scale, you're at a significantly smaller size scale than that. So that would be very, very small. If you're a bulk defect, meaning if you are a 3-dimensional defect, you must obviously be related with more than 1 atom, and these can have sizes of up to centimeters or meters. So bulk defects, you might imagine you'd be able to see with your eyes, some of them at least. And line and interface defects are smaller than bulk defects, but larger than point defects. And line defects are where you have a line, so it's related with a line of atoms, or a 1-dimensional chain of atoms. And an interface defect is when you have a plane of atoms. So maybe the larger interfacial defects you could see, but the other ones you can't, and line defects you probably couldn't see. Because what you can see with your bare eyes is generally said to be about 0.1 millimeters. And this is if this is the diameter of a human hair, approximately. So you get the idea that most of these defects you never get to see with your bare eyes. Some of them you might be able to see with special microscopes, and some you probably wouldn't even be able to see with microscopes. So a point defect is rather simple. You have a defect related with an atom. So if an atom is missing, or if it's in a place that it's not supposed to be in the lattice structure, then this is a point defect. So you have atoms that are referred to as being in interstices, meaning positions between regular positions in the 3-dimensional lattice. So self-interstitial or self-interstitial atoms are those that are removed from their correct places and are now in the wrong place. So in the case of an FCC structure, one atom that's supposed to be at a corner, if it moves slightly towards the middle of one edge of the cube structure, then it would be farther from one neighbor and closer to the other neighbor than originally. And this would cause some changes in the interaction that those atoms have with each other. So another example of a point defect is an impurity atom. So you have in an iron structure, with a cubic unit cell and atoms placed in particular positions, you suddenly have, in place of one of the iron atoms, you have some other atom. So this could be an example of an impurity atom. And depending on whether the atom replaces the original atom in its regular position, say a corner, or whether it replaces it in some other position, the names become different, so substitutional or interstitial. And one point defect, of course, could be the overall absence of a matrix atom. So you have a vacancy, you have the lack of a regularly expected iron atom at the corner of the unit cell. So you may say, what do I have if I don't have that corner atom? You have nothing. You have a space. And because you have a space, now the atom that used to be there is no longer there, and the attraction and repulsion between that atom and its neighbors has now changed because there is no atom at that position. So you may imagine that the spacing of the neighboring atoms will be affected by either the removal of that atom or its replacement with an impurity atom. So a self-interstitial here is said to be an extra atom that has crowded its way into an interstitial void. And these generally occur in low concentrations in metals because they distort the lattice structure. They cause, here it says stresses, but let's say it causes discomfort in the lattice structure. And a vacancy is an empty space where an atom should be, but is missing. And it's common at high temperatures when atoms randomly change positions, leaving behind empty sites. So then when that solidifies, you may end up with a vacancy. In most cases, the diffusion of atoms or mass transport movement of atoms from one side to another can happen because of these vacancies or causing these vacancies. So then the image on the bottom right-hand side shows the effect that a vacancy has on a two-dimensional representation of a metal crystal. Here I say metal because it's atoms of the same type or size, hence it's a metal being represented. And on the left-hand side, you have an example of a self-interstitial defect. So you see that in both cases, the planes or the lines have been distorted, but they've been distorted in a different way. So in the left-hand side, in the left-hand image, there is the four atoms. These four have been pushed away from each other, farther away than they used to be. And in this case, these four atoms have been pulled closer together compared with their original positions without a vacancy. So these two cases would be referred to later as zones where you have a compression and tension, or a pushing and a pulling on the structure. So although the structure is at rest and free from outside disturbances, outside loads, outside forces, inside the material, there are forces that have been locked in. So this is an example of how a point defect can change properties of the mechanical properties of a crystal. So then in a real life material, you wouldn't expect to have only one point defect, but you would have many, many, many point defects. And in this representation, again, here you see self-interstitial and a vacancy. So the substitutional impurity that we mentioned as being a foreign atom can either replace the original atom So in this image here, the gray original atom has been replaced by the orange new and slightly different sized atom. But you notice here that in the substitutional case, the foreign atom is about the same size as the atom it's replacing. So an example of this is shown as zinc in brass. So brass is an alloy that contains copper and zinc, and it has mostly copper atoms, and some of those atoms have been replaced with zinc atoms because the atoms are similar in radius. They're able to replace the original positions. When you have a very big difference in the atomic sizes, so you have much smaller atoms than in the bulk matrix for the impurity, like in this case, you have interstitial impurities. You can have interstitial impurities because this orange atom can fit in this small space, whereas the orange atom in this case can't fit in this space, so it has to cause some other change. So as you see, although it might be overly simplistic, it is really the case that atomic packing is related very closely with sizes of atoms or ions. So now, of course, bonding here in a metal or in an alloy of many metals is possible because you have, for all these metals, you have free electrons, or you have this shared pool of electrons, so they're all able to come together because they're of the same type. But of course, if you put in suddenly an impurity here of an element that was not a metal, then you would end up with different problems or different scenarios. So the ability for atoms to coexist or to exist side by side and to bond is important. And secondarily, the relative sizes of atoms are important in determining what patterns or lack of patterns can be achieved. So an example of an interstitial impurity in real life is the production of steel, an important construction material. And intentionally, carbon is added to iron. And as carbon is added to iron, the very small radius of carbon compared with the large radius of the iron atoms allows some interstitial point defects to form. I said carbon is intentionally added to iron, but if you actually look in books, or if you take follow-up courses, you'd see that in reality, although I say that, the amount of carbon in steel is generally obtained by reducing the amount of carbon from the original case. So iron is generally obtained with carbon mixed into it, and the amount is reduced until a desirable amount remains, and those remain partly as these interstitial defects. So when metals are brought together, they form either of these two types of alloys, or are full of these types of defects that we mentioned, or one might also say they have both simultaneously. So again, if you have multiple elements, they may form both substitutional and interstitial defects within the structure. So this is all for metallic structures, because metals can get together. They're all the same in charge. They're all positively charged cations, and they are swimming in this sea of electrons. But in the case of ionic structures, you have a plus minus arrangement. And you may imagine that if you have a vacancy, as shown here, which is in an ionic structure, referred to with this special proper name of Schottky defect, not only one atom is missing, but two ions are missing because one is positively charged. And for electrical neutrality, you need 1 plus and 1 negative to be charged, to be missing. Another type of defect, called a Frenkel defect, is when an anion or a cation is at an interstitial site. So this is quite similar to the case on the previous slides. But again, notice that here, overall, there is an electrical neutrality achieved, which is important for the structure to be stable. Now, when you go up to 1 dimension, the line defects are described also with the name dislocations. And this is defined as the slide or slip of a portion of the crystal over another portion. And these dislocations move one part of the system relative to the other. And through this movement of dislocations through the whole system, the system is able to deform permanently. So 1-dimensional defects are extremely important in that they define how or why a metal is able to bend permanently. But otherwise, of course, because you can't see this, it's difficult to follow, despite its very great importance in defining the whole idea of deformation in crystalline structures. So dislocations are at the boundary between regions where some slip or some deformation has happened and where it has not. And on either side of a dislocation, the crystal system is perfect. So essentially, a dislocation separates one part of the crystal that is perfect from another part that is perfect but shifted by 1, 2, or more atomic spacings with respect to its original position. So the strength and the ductility, which is a fancy term that we discuss later for ability to deform without breaking, so the ability to bend, is controlled by these dislocations and their movements. So there are 2 types of dislocations, and they're shown on this slide. They're referred to as edge and screw dislocations, and the difference is in the geometrical way that the structure deforms. So in the screw dislocation type, there is a movement that shifts one portion of the crystal with respect to the other portion, and the amount of movement or the amount of distortion on the 3-dimensional lattice is shown with what's referred to as the Berger's vector. So the Berger's vector in this case is the vector that completes this loop around the dislocation. So you draw, you count the number of jumps from atom to atom around the dislocation area, and you see that there are 4 jumps here, 4 jumps here, 4 jumps here, but there are 5 jumps, an extra jump needed, indicating that there is an extra line of or extra plane of atoms here. So this, and this series of atoms continues, but this one does not continue. There's no continuation of this line below the dislocation here. So then this is referred to as an extra half plane. Here's the half plane, because it's, you can't, I'll see on, so this is the top and side of this plane, this two-dimensional plane here, inserted into the crystal structure. So the idea is the material is deforming due to some outside force application. And as you say, push from this direction and push from this direction, the material shifts by one, or let's say in this case, by pushing from this direction and this direction, this extra half plane is moving towards the left of the slide. And as you keep pushing, this bond here, or all of the bonds along the line from this point into the slide, so the line here, will break, and they will rebond with this half plane, and this location here will have shifted to this point, and then with some more pushing it'll shift here, and then with more pushing it'll shift here, and eventually the whole top portion of what was originally a square will have shifted 1 unit to this side, and this bottom portion will have shifted in relation by 1 unit to this side. And if you keep pushing more and more, then you could get more deformation within the structure. Now, the screw dislocation shown here is also discussed using an amount or a magnitude of this distortion. And the Berger's vector, again, completes an imaginary square drawn around the dislocation line. So notice that the dislocation line and the vector are parallel to each other, whereas in the case of the edge dislocation, the dislocation line is here, and the Berger's vector is perpendicular to the dislocation line. So you might look at the two images and you might say they look very similar. So what's the significance of this? And the idea is that you're right in that they're very similar because they would describe, they'd be able to describe the how one can obtain in a crystal this 3D network of atoms, this final structure, or this final structure, by applying a stress, a force, let's say simply, on the original cube structure. So the difference is that in one case, the forces applied cause movement by the bonds here breaking and new bonds being formed, and then those breaking and new bonds being formed until the material. So the original bonds between the atoms here and the atoms right above them are broken, and this happens along this whole line, and new bonds are formed here. So if we kept pushing the top portion to the right and the bottom portion to the left, we would then get one more step, or the step here would get wider, and the Berger's vector would indicate not one atom length, but 2 atom lengths of a distortion or movement. And the direction of motion is hence along this applied stress, whereas this is like a screwing action, hence called a screw dislocation. But notice that the two can give you, depending on the types of forces applied on the structure, on the crystal structure, they can give you the same final outcome, but through different intermediate steps. So here, what you should understand is that these dislocations are what allows atoms to move relative to each other in let's say one-dimensionally, or in as lines of atoms. Now, something important to grasp here is that in metals, this dislocation motion, or this deformation, or this ability to bend is possible, or it's easy. It's the ability is high because the bonds are, as we discussed in the previous slide sets, non-directional. Because the atoms don't care about the orientations of their neighbors, but they rather want to maximize their number of neighbors, they are able to break their bonds with some of their neighbors and reform bonds with new neighbors. So the ability of a metal to bend before breaking is due to, and due mainly to, the fact that it doesn't care who its neighbor is. So as long as it finds a new neighbor, it's able to bond with that new neighbor. Hence, it's able to form a new strong structure in its new shifted position. But in the case of covalent materials, or ceramics, like diamond, the dislocation motion is difficult because the bonding is directional, or the angles at which the bonds need to be made are specific. So in diamond, they're well-determined angles between the different carbon-carbon bonds of the tetrahedral structure. So because of this, when you want to break one of the bonds, because the structure does not want to have new bonds at some other random orientation, but wants to keep atom pairs or these bonds at certain angles to each other, the resistance is very high. But once this is broken, the material does not want to shift to a new position. Hence, covalently bonded materials will not be able to bend like metals, despite the fact that they are very difficult to break. They will break without bending. So this slide is actually quite significant in that, similarly, ionic ceramics or ionic materials like sodium chloride can also be strong because ionic bonds are strong, but they will not want to move. Atoms, rows of atoms, will not want to move with respect to each other because you may imagine that once you move this top row with respect to the middle row, two positive charges and two negative charges will be closer together than they originally were, and they will try to push each other strongly, and this top portion, the top row, will break apart from the middle row. So it is very difficult to break these strong ionic ceramics, ionic materials, ionically bonded materials, but they will again break without bending. This slide very simply explains or gives the answer to the question, can I make a material that is not a metal bend? Or why can't I make a non-metal bend? Now, there is an exception here, and that is the case of polymers. So we haven't formally discussed that, but because we said polymers are covalently bonded, but also weak bonded, with van der Waals bonds. The weak bonds in a polymer will allow you to bend polymers. Hence, they will also, through that property or through that characteristic, be able to bend. So then, in addition to metals, polymers will bend, but covalent and ionic materials, so covalent only or ionic only materials, will not bend. And it is pretty safe to say that they just will not bend, and there is no real simple solution to this. So this is a limit that we have. And this slide explains very simplistically, but very effectively, why this cannot happen. So in 2 dimensions, we have what we refer to as interfaces, or planes coming together. So you might think of this as your left hand and your right hand coming together and touching each other at the palms, and or the palms and the fingers touching each other. So this would be an example of an interface. And if there's a problem where these two meet each other, a problem here again defined as the change in the interaction between neighboring atoms, this would be referred to as an interfacial defect. And this again affects many properties, and it could again be intentional. So it could be a part of the thermal or mechanical, so heat or force related treatment of a material to obtain changes in the atomic order to get desirable properties, as well as being natural and unwanted. So there are many, many examples of these. We'll focus on a few of them. So very simply, the surface of a crystalline material will be an example of a 2D defect. So notice that all the spheres here, so the top is the surface, and the bottom just represents the continuation of the material. So imagine that the material has the same atoms here. It's just drawn, it's not drawn for simplicity, but this top surface is the top surface of the crystalline material. It's the outside surface. And this atom has the same, or let's say this atom has the same size as this atom, because it has a pull and a push between its neighbors. This atom is slightly different because it's the second row, and this atom here, where all the atoms on the first row at the surface are slightly drawn slightly differently here. And the reason for that is not really that the atom is distorted into an elliptical shape, but to indicate that because there is no fourth atom to pull on this surface atom, there is a difference in the feeling of this surface atom. So instead of being pulled and pushed by 4 neighbors, it's being pulled and pushed by 3 close neighbors. Hence, it behaves differently than this. Because this is a weird, different atom, its effect on its neighbor, the second row, is slightly visible. But after a certain number of rows of atoms, you see that all these 4 bottom rows, this row, this row, this row, this row, they're all the same. Because this atom is pushed and pulled by its 4 neighbors, and this atom similarly, and this atom similarly. So you see that even being at the surface of a material could change, could cause some changes, good or bad, in order. Now, 2 more complex examples of these are when here shown in two dimensions, but imagine because this is an interface, it's a face, it's like the insides of your 2 hands meeting each other. You may think that these structures, these unit cells, continue into the slide. So when this top portion, a crystal growing from this direction downwards or towards this blue line or blue boundary, the line actually represents a plane into the slide. And when this this crystal and this crystal meet, they form a boundary. And depending on the particular properties of the boundaries, you can get different properties, and you can get different names, you can give different names to them. So in the special case where there's some sort of a symmetry, you refer to this as a twin boundary. And in this other case, where you have two different crystals growing from here the left, right, and here from the right to the left, and here from the left to the right, when they meet, they will join, but they will have half planes of atoms, as you can see, that form as a series a boundary, which is referred to as a tilt boundary, because this portion and this portion are tilted with respect to one another. And if you were to look at this triangle here, you could calculate that there is actually an angle of tilt. And in crystallography, it is of significance. So different materials, when growing crystals that meet each other at some common interface, depending on this angle, depending on their properties, they tend to form at different angles, this boundary, and depending on the angle, you tend to get different structures. But this is way too complicated for this course. But it's important to realize that this series of edge dislocations that we showed on the previous slides, this collection of edge dislocations shown by this perpendicularity symbol is what makes it possible to join a crystal and another crystal at an angle to each other. So an important example of this, of these boundaries, is when you have grains or crystals in polycrystalline materials that grow, as we had discussed earlier, from certain points outward. So this grain grows from, say, this point outwards in all directions, and this grain here grows outwards from its center, and this one does the same. And when they meet, because of where they start, because units, because grain B starts from a different point than grain A, they don't necessarily grow with the same unit cell orientation. So this unit cell is identical to this unit cell, but they grow in different orientations, so that when they meet along the grain boundary, there will be an angle between the two individual crystals. And hence, the properties here, and the properties here, and the properties here at the centers or far from the boundaries are identical. But at the boundary, there will be different properties, because the average spacing between atoms will be different than in the middle portions of the grains. And if you take a real material, in this case brass and alloy, and if you polish it and you look at it under a microscope, here it says this black line represents 90 micrometers, 0.09 millimeters. You see that you have these irregular shapes. Each of these is a different crystal. So it's this shown in reality. So the different portions are, they look different in color. They're not actually all that different. They're all actually the same, but they are oriented differently. And here, because of this, when they meet, they have boundaries. And you might imagine that if boundaries are important in determining properties, the total length of boundaries in a total area of the material, or in a three-dimensional volume of the material, the total length, the total area of the two-dimensional boundaries would depend on the average size of the grains, So for smaller average grain size, you would get higher surface area, higher area of the interfaces or the boundaries. And for larger grains, larger average grain size in a material, you would get a smaller total area between the grains, or a smaller total boundary area. So because of this, for the same material, say iron, if you process it during its growth slightly differently, you could get larger or smaller crystal sizes on average. You would not be able to grow the crystals so that they all have the same exact size, like shown here. Some of the crystals will end up being smaller, and some of them will be larger, and some of them will be even larger, but they will be randomly shaped, and they will have some sort of average size. And if the average size is smaller or larger, the properties of this so-called same material, iron, will differ. Now, when you go to 3 dimensions, bulk defects are much larger than all of the other crystal defects, and they too influence the movement of dislocations, hence the movement of the ability for the material to, say, bend. And the idea here is that to be able to bend from 1D to 2D, you saw that you needed for rows of atoms to move with respect to their initial neighbors due to some sort of applied force. And when you have atoms moving along and suddenly they reach a zone where there is a 3-dimensional problem, this will disturb this movement, and it will make the movement, say, happen more easily or restrict the movement. Hence, 3-dimensional defects are extremely important. And one reason why they're extremely important is because also they are very, very large. You may imagine that if they are, say, a millimeter by a millimeter by a millimeter, this would mean that, and if an atom on average is 0.1 nanometers, then you might imagine that you have along a cube, a hypothetical cube volume of 1 millimeter by 1 millimeter by 1 millimeter, you have 10 to the 7 atoms that could be placed side by side. And you have 10 to the 7 times 10 to the 7 times 10 to the 7 atoms in the cube, which would mean you have 10 to the 21 atoms in a space that is only 1 cubic millimeter. So you may have a different distribution of atoms than this, but you may imagine that the number of atoms that you have is easily a billion times several more zeros. So because of this, when you have a large crack or a void or a problem in your material, in your crystal or in your overall material, you will have a significant influence on overall properties. And if you ask, what size impurities does a civil engineer need to care most about? The answer is volume defects. And the reason for this is because they are very large. So cracks, holes, notches, etc., in materials that are able to break without bending, so-called brittle materials like glass, not an example of a crystal, but nonetheless, would cause a great difference in behavior. In that if you have a defect-free sample of the material, and if you have a defective sample with bulk defects, you would see that the defective sample would break unexpectedly at very low levels of discomfort, at very much lower forces applied than otherwise. So voids are an example. They're regions where many atoms are missing. So what might be the reason for this? During production of, say, a molten material, like a molten metal, for whatever reason, if you have an air bubble that gets trapped inside this molten metal, then this air bubble will not have a very large number of atoms in it, and it won't have any of these metallic bonds inside it, so it will cause a void. And so pores are examples of these. You can also have what are referred to as inclusions. So when you have inside your molten metal, you accidentally drop something, say a small size, you drop, say, crumbs of a material, you drop powder of some other material. So this remaining in the solidifying metal would cause a three-dimensional zone. Each powder particle that you dropped accidentally into the, or intentionally, into the molten metal would remain there as the metal solidifies. And around the powder particle, you would have the metal three-dimensional lattice. And the powder particle itself would have some other properties. And as a line of atoms are trying to move through the metal, when the turn comes to this line of atoms trying to move through this inclusion, this powder particle, it would not move. Either it wouldn't be able to move if it were a very strong material, or it would move with a different amount of difficulty, and it would cause changes in behavior. So to finish up this video on crystal imperfections, I want to show this example of that gets discussed in some other classes later on, but the sample of how bulk defects can lead to what is referred to as stress concentration. So the stress concentration here, stress gets defined later on in this class, pretty soon, in a few weeks, but a stress is an equivalent of pressure from previous classes, from high school. So here a concentration is the focusing of greater than usual pressure at a certain point inside the material. So let's start with an imaginary plate shown in yellow. So you can have in this plate the absence or the presence of a hole. So if you were to start with a plate, a rectangular plate, and pull on it from two sides in opposite directions, if there were no hole, what would happen is possible to represent as such without a hole. You would essentially, along this line, this imaginary line that goes through the material, you would have an equal amount of pulling, or an equal distribution of force along this imaginary line without the hole. If you had a hole, and it would be in amount equivalent to what is being applied on the left-hand side, pulling the half of this plate, this imaginary half plate, in this direction. And the reason for this is because if you pull with more force on the left than on the right, then the material will move towards the left, or the plate will move towards the left. So you need to have some sort of force balance, some sort of pulling balance. So on this, in this case, with the hole, because there is a hole here, at this imaginary line, there is no ability for force to be applied here. So here there is zero force and there is zero pulling. So then this total amount of force applied over this line, on this line, over this length, needs to be applied by the summation of the total force applied here and the total force applied here. Now, because of this, you might imagine that the amount of force average applied on the left needs to not be equal to the force applied here, because the force applied here combined with the force applied here needs to balance this force applied here. Hence, there needs to be some sort of uneven distribution of force. And what is observed, and this is calculable, but of course it's kind of early in your coursework for that. What is calculable is that the amount of pressure applied at the points shown in red, this point and this point, happens to be 3 times the magnitude, 3 times the value of pressure applied on average on this side. So the pressure distribution or the force distribution or the unhappiness distribution here along this portion of the plate, the middle of the plate, is uneven. And it's uneven in the sense that the most unhappiness is felt here. So you might imagine that if you keep pulling on the left and on the right, the very first place, the very first portion of the plate to break will be this point and this point.